where we left off, we last left by me having you do a problem. Hold on while the screen shows up. Where's my whiteboard? Dang it. Show up. There it is. So we wanted you to find the nth term of this sequence that I gave you here. And it's a relatively easy problem. So the solution, obviously, n is equal to 1, 2, 3, 4. And of course we have a sub n, which is of course 1, 3, 5, 7, which you can see here. It ends at d in the situation 2n minus 1. So you can see how it's twice n. A sub n is equal to 2n minus 1. Because it's 1 less than me multiplying it by 2. Okay, so that's how I define it to be 2n minus 1. You don't have to use this table, but I find that it helps sometimes to be able to look at a situation. Okay. There is such thing as a recursive sequence, which is defining it in terms of another. Defining in terms of another. That's the idea of what a recursive sequence is. And with the famous recursive sequence is, of course, the Fibonacci sequence. And we know how this works. I'm not going to do it. It's an example in the book, which is already done. So, but I will do an example of a recursive sequence here. Oops, didn't switch the pen color. So, I want you to find four terms of the recursive sequence. Okay. Yeah. A sub 1 is equal to 15. And then we have a sub k plus 1 equals a sub k plus 3. Okay. You'll notice we don't define exactly what a recursive sequence is. But recursive is when we write it in terms of the previous. So here, I can see a sub 1 is 15. So if I plug in 1 into this equation, I get a sub 2 is equal to a sub 1 plus 3. Simple enough, right? Because if I define k to be 1, plug it in, we get a sub 2 is 15 plus 3, which is of course 18. And likewise, it continues as such. A sub 3 is going to equal a sub 2 plus 3. So a sub 3 is equal to 18 plus 3, which is 21. And if you haven't noticed that this takes on a pattern, it ends up being the previous term plus 3, which is 24. That's a sub 4. And then a sub 5 is equal to 24 plus 3, 27. So the idea of recursive sequence is that it's defined in terms of the previous number in the sequence. As you can see here, this becomes this, that becomes this turn here, and becomes that turn here, and so on and so forth, and that's how it will always be with a recursive sequence. Okay. Now moving on to factorial notations. With factorial notations, we have this way of kind of doing things which makes our lives a little bit less painful. Because let's face it, who in the wants to write something like this? That's a lot of numbers. I can go times 11. Times 16, for example. I have all these numbers written out, and writing it out becomes a little bit of a pain in the butt. And so to make this easier for us, we define what we call factorial notation. Okay. And if I rewrote this as 16 times 15 times 14 times 13 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, it's a lot of numbers. So we define this factorial notation to be So we define it if n is an element of positive integers. So the double line z, of course, needs the positive integers. So we define n factorial, which is the little exclamation point on your calculator, is equal to n times n minus 1 times dot 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 times 3 times 2 times 1. Okay. And we define also 0 factorial to be 1. Okay. And there is a reason for that definition, which we will find out later. And I don't have the ability to tell you that now. Right. So this notation allows us to write and do things involving sequential multiplication really quickly, and instead of having to write all of that out. Okay. So for example, I know that 2 factorial is equal to 2. 3 factorial is equal to 3 times 2, which is equal to, of course, 6. 4 factorial is 24. 5 factorial is 120. And 6 factorial is 720, for example, something like that. Now, you may ask, how did I do that so quickly in my head? Because I'm so used to viewing all these numbers, it becomes relatively easy. Now, the rules for factorials also apply, meaning that, for example, some number m times n factorial means I multiply n, then do the factorial here. Alright? But if I multiply by any number n, factorial is of course mn times nn minus 1 factorial. And so on and so forth. Okay? So let's work with this notation and figure out how to solve the problem. Another example here. Let's find the first 4 terms of the sequence a sub n is equal to 3 to the n over n factorial. And when we're working with factorials, we want to start with 0. So when we're working with factorials, we always start with n equals 0. Okay, because 0 factorial is 1. So a sub 0 is equal to 3 to the 0 over 0 factorial, which is 1 over 1, which is of course 1. A sub 1 is equal to 3 to the first over 1 factorial, which is 3. A sub 2 is equal to 3 squared over 2 factorial, which is 9 divided by 2. And then a sub 3 is, of course, 3 over 3 factorial, which is 27 divided by 24, which, of course, can be simplified to 9 over 8. Okay, simple enough. Alright, so let's see. Well, let's evaluate a factorial expression. Nine factorial over 3 factorial and 7 factorial, for example. So to evaluate this, I, for one, do not like to use calculators. We can avoid them. We can actually do a lot of simplification by knowing the rules of factorials. So watch this. So our solution, we write it in terms of the largest factorial. In terms of the largest factorial. On the bottom. So in this case, 7 factorial is the largest. So in this situation, 9 factorial becomes 9 times 8 times 7 factorial over 3 factorial times 7 factorial. 7 factorial is the same. Cancels. Die. Wah! Now you're left with 3 factorial, which is of course 6. So we end up with 9 times 8 over 3 times 2. That kills that 4 times, that kills that 3 times. So we end up with 4 times 3, which is of course 12. Lovely. So I'm going to leave you to evaluate another expression, and then when we come back, we'll talk about sigma notation. So I will leave you to evaluate that, and when we come back,